I would like to invite Dr. Jean Riviere. He is professor of director of the Chemical Center Research in Pharmacokinetics and Toxicology of the vet faculty in North Carolina. He is elected in the Institute of Medicine of National Academies and works at the Food and Nutrition Board, and is also a member of the Pi Beta K Sigma in the Administration of Foods and Medication. In 1999, he got the Maxi Gassner Award of the North Carolina University. 1991, Ebert Award of the American Association of Pharmaceuticals, and the Harvey Double Willie Medal with a special mention to the FGA Lifetime Achievement Award of the European Association of Pharmacology and Toxicology in Vet. Biomathematician, Science and Mathematics at INSU, was official in several sessions of toxicology and editorial councils of magazines of toxicology, vet, and pharmacology. He produced more than 430 papers and research chapters, and wrote 10 different books. Received more than $16 million as main researcher in fellowships using animal models by mathematical models, risk evaluation of pharmacokinetics, nanomaterials, absorption of drugs and chemicals by means of skin, food security, safety.
Thank you very much for the kind introduction, and thank the organizers for inviting me. What I would like to do today is to shift gears a little bit and go back to some of the actual earlier presentations and talk about biodistribution of nanomaterials, and specifically trying to look at methods and ways that we can learn to actually quantitate and characterize materials so we can extrapolate across materials and across different model systems. Realistic risk assessments of nanomaterials require some type of a quantitative framework to allow extrapolation between systems and particles. It's important in the early phases of nanotoxicology to demonstrate descriptive studies, to demonstrate hazard, to demonstrate what may actually occur. But as we move forward in the process, we want to be able to learn to extrapolate some of this information to a novel particle. And some of the earlier presentations this morning looking at nanomedicines and looking at targeting nanomedicines depending on a type of proteins, it's this kind of work that we want to explore. We hope that many of the existing particle characterization studies used now are really based on material science determinations. They have direct application to inhalational studies where the particle is interacting with air. But when you get into a biological environment where the particle is interacting with an aqueous environment, it's a little bit different. And the type of physical chemical properties that describe particle interactions in air or at high temperatures may not necessarily be relevant to interactions of a particle in an aqueous environment with proteins and other biomolecules present. So what I'm going to talk about is pretty much go into looking at this on work we've done, looking at 3 different approaches. One is to look at an ex vivo isolated tissue preparation to see if we could use this to study biodistribution of particles. In this case, we can control what type of meteor, what type of perfusate we can look at, and we can measure the uptake into tissues under very controlled conditions. This also provides data in the context of what I'm going to try to present to you, which is physiological-based pharmacokinetic models. That is an approach used in organic molecular chemical risk assessment to pretty much quantitate dose and target dose to the potential target organ. So what we've done, and I'm going to review some studies we've done over the last couple of years, is to basically see, so can we even apply this to nanoparticles? and just to give some indication of where nanoparticles may be different than organic chemicals. And in the process of developing this work, we realized, as Dr. Montero said earlier today, that the surface characteristics of the particle are really important. So we shifted gears a couple of years ago as we were generating this data and realized we need to come up with a biological metric, measurement, parameter that somehow correlates what a nanoparticle looks like relative to interactions with biological systems. And instead of looking at high reactivity, high temperature surface interactions and chemical reactivity, we're looking at absorption problems. In other words, we're trying to come up with like an octanol water partition coefficient, which is used to predict chemical deposition and activity, come up with a surrogate of that for nanoparticles that also picks up other important biophysical interactions. And I'm going to end with that presentation. So biodistribution. We heard before about inhalational studies, where essentially if the compound is actually inhaled and if there's some surface, if there's some internalization of the particle, that you actually get systemic distribution. What we've been focused on is what happens if the compound is actually absorbed, either after an oral route, after a dermal route, gets into the systemic circulation, what can happen to it? This is a domain of pharmacokinetics. What I want to do is just try to give some perspective as to what can we actually look at and the approach we can look at to model this. We have to realize that unlike just chemicals, the lymphatic system is another system that is designed to basically take very lipophilic particulate matter and move it around the body, because this normally is what is presented in the body. It's viruses, bacteria that are particulate, that are handled differently than chemicals in solution. So this is something that people have begun to look at, that it's possible that lymphatic trafficking occurs for a lot of nanoparticles. And if we just use blood-borne studies, we don't even see any of that. So again, it's just a general framework that I'm going to try to pull together. And what I want to first focus on is let's just look at a tissue and look at a capillary bed perfusing a tissue, and can we look at uptake of nanomaterials in this area. Dr. Montero mentioned before about doing dermal absorption studies. So we're in the same group, and obviously we've been doing a lot of dermal absorption studies. One model system we worked up probably 20 years ago that has a very direct correlation to human absorption and disposition is the isolated perfused porcine skin flap. But what I'm going to talk about here is not looking at absorption through the skin. I'm going to look at it inside out and essentially look at what happens if you perfuse a material into the artery, and then what happens to the uptake of the tissue and what comes up the venous drainage. This system has complete control, again, over physiological parameters and perfusate composition. And what's unique about it is it has an intact capillary microcirculation. We've done 20 years of studies showing that if we put a vasoactive compound, a vasodilator, a vasoconstrictor, that we can modulate uptake of compounds, that we can play around with the pharmacology of these type of systems, and we can modulate pretty much the microvascular uptake. So it looked to us that this is an ideal system to study nanoparticle biodistribution, because at the final phase, you're essentially looking at a nanoparticle in blood, either in solution or bound to something. Will it actually get out of the tissue? Now, we know that for a large amount of nanomaterials, phagocytosis will occur. But this tissue doesn't have a phagocytic system intact. So what we're looking at is that other small fraction nanomaterials that people always find in vivo that get into various tissues, and can they actually be taken up by tissue, either by diffusion or by uptake into endothelial cells. So I'm sure you'll find some interesting results on this. The system is a two-stage surgical procedure where we create two skin flaps on the ventral abdomen of a pig that are perfused by a specific artery. We come back 2 days later and cannulate that artery, take the system and put it into a perfusion system in which we now perfuse the artery, and we can measure the arterial and the venous concentrations. And if you're a pharmacokineticist like I am, this works out great, because what you can do is actually measure the arterial venous extraction in a viable perfused tissue bed. You could control what you put inside the media, Like I'll show you one example where we put IgG, or we did not put IgG in a meteor, and did this make a difference in uptake of particles? We can perfuse these things for like 24 hours. A lot of the studies we've done are only occurring over about 8 hours because we pretty much reach equilibrium in the data we want. This is the actual example of the perfusion chamber. The whole thing is pretty much computer monitored. We can control everything we want to control. So the flap sits here with an arterial perfusate going in. And a long time ago, we did a barium angiography to determine where we actually perfuse in the capillary beds, and we are. So what we're looking at now is infusing into the artery a nanomaterial in solution, and then measuring the arterial venous extraction of that compound. The initial studies we did were using quantum dot 621. This was the same type of material that Dr. Monteiro mentioned on dermal absorption, with 2 surface coatings, either PEG or carboxylated coating. We infused it at 3 different concentrations of 1.6, 3.3, or 6.67 nanomoles for 4 hours, followed by infusion of a clean perfusate. We had done numerous studies before of chemical deposition. We use this a lot to look at reactive platinum chemotherapeutics binding to a perfused tissue bed, or a perfused tissue bed with a tumor growing in it. So we had been working on this type of system for a long time. And pretty much this gives us the best solution to the model. Again, we measure arterial and venous concentrations. We use both a fluorescent assay because we had quantum dots, and we also quantified the cadmium and got a reasonable correlation. Remember, you're never going to get a one-to-one correlation because a quantum dot doesn't have a uniform amount of cadmium per quantum dot. There's always a splay in there. So whenever you're trying to extrapolate between a fluorescent endpoint on nanomaterials with quantum dots to an actual quantitation, you have to actually have a little splay in there. You really need to know how much cadmium and how much cadmium per quantum dot. Also, quenching occurs with fluorescent studies. If you leave these compounds interact with molecules for a long period of time, the interaction of the molecule with the surface will alter its fluorescence. And that's something else that needs to be taken into account. But for the duration of our experiments, there were no quenching observed. Okay, I'm going to try to be very simple on some pharmacokinetic models. So the whole point of this is we want to come up with a number that says if we infuse with a quantum dot PEG-coated or a carboxy-coated, is there any difference in tissue distribution? So we essentially create a very simple model looking at the rate constants going from the artery into the vascular bed of the skin flap and perfused skin flap versus what comes up the venous effluent. And then we basically look at this number, which is the primary rate of uptake from the vascular to the tissue bed, this K23. So this is telling you when there's actually tissue uptake. You then solve these models by writing a series of differential equations. Again, very, very straightforward, a very simple model. We have a lot of data, so we can make a reasonable estimate of what all these parameters are. If you look at the actual experimental data, looking at the 3 concentrations and the 2 types, you essentially have a model fit. I want you to note here that the mean fits pretty good, but notice this lot of splay, and I'm going to talk about this later, of what looks like random noise around these fits, and it turns out it really isn't all that random. Okay, you do all this, you run up and you do the pharmacokinetic analysis, and in looking at this, we noticed that there was a significant difference on the carboxy-coated particles, in which K23, which is that uptake into tissues, was higher. And when you look at the ratio of uptake versus release from tissues, you notice it was 2 to 3 times higher than the PEG. So here goes a system looking at tissue distribution with everything else that could happen, that once when the particle gets into the vasculature, you have a preferential uptake of the carboxy nanomaterials. This is without phagocytosis occurring and without opsonization binding to other types of proteins. If you then follow, Nancy did some electron microscopy looking at a vascular bed and looking actually within an endothelial cell, and you can see that actually these particles are taken up and sequestered within the endothelial cell. Now when it comes to risk and hazard, this is interesting. There's not a lot of particles here, but do you really want a lot of cadmium-based quantum dots floating around in your vascular endothelial cells, which do not actually have a high turnover rate? If you then look at the two rates again on the carboxy extraction ratios are pegged, the carboxys are lower because some of this tissue, some of this compound is actually going into the tissue. We also realized that there was a pattern when we actually combined this data, and we noticed that there's a sinusoidal uptake. And this is fascinating. What this means is that there's a periodicity in the arteriovenous uptake. There's been some other pharmacokinetic studies published by quantum dots that suggest that you get a redistribution phenomenon occurring, which means that if you basically have an in vivo exposure, say by intravascular administration, and a compound ends off in one tissue, if you look at it over a period of time, the compound ends off in another tissue later on. So what is the driving force for this? In some lines, it may be due to this vascular redistribution, and I'll also indicate it may be due to agglomeration and disagglomeration. Very, very, very different phenomena than seen with chemicals. This just doesn't happen with chemicals. We then looked at NC60 into a perfused bed and basically looked at a way that we're going to be doing a physiological-based modeling. We infuse it into the artery, we see what comes out of the vein, and essentially we're looking at what's actually then taken up into the volume of the skin flap. In this case, we analyzed the fullerenes using high-performance liquid chromatography, so now we have a very specific assay for specifically how much fullerenes are actually taken in. And again, we use a slightly different model that's more compatible with the PBPK work. Again, a very homogeneous sized nanomaterial, someplace around 10 nanometers. And in this case, we had less tissue uptake. We looked at IgG plus and IgG minus media. I'm just showing you this slide because we thought there was an effect. In reality, there wasn't much of an effect. But this illustrates how you can use this type models to look at what type of potential factors may modulate tissue uptake. When you look at the actual uptake, probably about 7 or 8% extraction occurs. This is a lot of extraction. I mean, it's not 80%, it's not as much as the quantum dots, but you're looking at a significant amount of NC60 being taken up into a perfused tissue bed, and not like what's occurring within kidney or liver, which would show a much higher extraction ratio because of the reticular endothelial cells. But again, these materials are being taken up into tissue. So the conclusions from the perfused tissue studies, this seems to be a relatively efficient model system for assessing biodistribution, enhanced uptake of the carboxy-coated quantum dots, and these model predicted uptake data was actually confirmed by confocal microscopy. Data could be normalized by dose, which suggests linear pharmacokinetics in this range, and no periodicity seen. We now look at what happens if we make a physiological-based pharmacokinetic model. Here's an example of what would happen with the skin flap, but now we'd be looking at other tissues, and then the goal is to make a model and predict what happens in these other tissues. Similar type equations, again, I don't want to spend a lot of time on this, but the rate factors and the rate equations are basically looking at an extraction ratio or a partitioning between the plasma and the tissues. We analyzed the QD705 data of Yang et al. In mice. All its organs had data that was going over a period of time, but what was fascinating is that in these organs, there was no elimination detected from these animals. In other words, people collected urine and feces, and there was actually no excretion of these quantum dots. So this was a different situation than we're normally looking at. We had measured related to the accumulated quantum dots in the organ as a function of flow and used a default physiological-based model that's used pretty much for a lot of chemicals, except there's no elimination. When we looked at this, our basic equations, again, are the blood flow times the arterial minus venous excretion, and we measure a partition coefficient by a ratio of plasma to tissue levels, normal units, and we modeled mice and rats for organ blood flow and organ size, and I'm just showing you this periodicity function because we played around with this also. This was the actual data collecting over 14 days in skin, muscle, kidney, liver, and blood. But what's interesting is here are the partition coefficients calculated on this. So you can see the liver had a much, much higher extraction as would be expected because of the RE cells, the kidney, the muscle, and the skin. When you actually look at how the model fit, good fitting for muscle, for liver, for blood, for skin, and something different is going on in the kidney that's not being picked up on these models. Part of the reason is it's going in the kidney, but they're not leaving the kidney, which is what would normally happen with chemicals. They're being accumulated within the kidney. When we then looked at the effect of periodicity, curiously, the only organ where periodicity had any effect by including this in our model is skin, which has reasons for it, because skin is a thermoregulatory organ, and it's used to changing blood flow dramatically, while other organs are not really designed like this. And when you look at other molecules, QD705 fit well. There are specific pathways where those particles are taken up. So when you start looking at the particle differences, it's not just the particle that's important, it's what is the particle bound to. And there's a lot of work with Ken Dawson on protein coroners, and I'm going to start mentioning that shortly. But we realized, but based on all these other models over here, why they're not fitting is because this process is different. And secondly, we know there's a periodicity issue. So now when you actually have to try to determine this, it's a permeability limited tissue uptake. And actually to know what the relative deposition of the chemical in the body is, it's probably not a function of the core properties of the nanomaterial, it's a property of the surface of what that nanomaterial looks like. When you actually also look at considerations, you have to think about agglomeration. And we know with these quantum dots that they agglomerate at low pH. So if you actually look at the size of the particle as a function of pH, when you're in physiological pH within a cytoplasm of the plasma, they're not agglomerated. But when the particle is taken up intracellularly into, say, a lysosomal compartment, then you're going to get agglomeration, and a particle is going to stick there. And this is a pretty reversible type process. So now you have to start realizing how the heck do we take into account that process in a PBPK model. So what I want to finish on my last 5 minutes is essentially to say that, okay, if interactions of the material with proteins and other biomolecules is important, we would like to figure out, can we actually characterize this surface? So we know that when a nanomaterial is in solution, it may bind to another nanomaterial and aggregate, or it may bind to other biomolecules. Those biomolecules could be amino acid residues on proteins, which essentially form a corona, or they could be other small molecules in the environment. And knowing mass, knowing surface area, knowing size tells you nothing at all about what type of interactions would occur. We need to now go and basically look at the nature of the biophysical interactions occurring in a biological environment. And these are weaker interactions. These are hydrophobic interactions, hydrogen bonding type interactions, charge interactions. So we came up with a method that was published a couple of months ago in Nature Nanotechnology on an index for characterizing these interactions. The primary goal is to identify the interactions on the surface absorption process, and essentially, could we come up with a quantitative assessment of this that could be applied across nanomaterials? We want a metric to determine how tissues actually see a nanoparticle in order to select the proper model to quantitate uptake. Because as Nancy mentioned on her cellular uptake studies in keratinocytes, which pathway of uptake occurs and the rate of the pathway of uptake occurs has to do in many cases with the size of the particle or the surface charge of the particle or specific surface active components that kick in certain uptake mechanisms. So what we need to know is what that outside surface looks like. And essentially to come up with a surrogate for an octanol water partition coefficient. It's really hard to determine a classic octanol water partition coefficient for a nanoparticle because you take octanol, you take water, you put the nanoparticle in, you shake it like this, everything aggregates off on the water side and it never even makes it to the other side. So you need to basically look at another interaction. How do we do this? We use a set of 28 small molecular probe compounds with a very, very different physicochemical properties. I could spend an hour talking about the kind of approach you would use on this. This is basically a quantitative structure activity model that essentially probes the binding of 28 different molecules from water to the nanoparticle. And so we essentially find out that if the particle is very lipophilic, then all the fat-soluble molecules essentially bind to the particle. None of the other ones do. And we vary that by using 28 different molecules. We get a reasonable presentation of the type of forces. The whole thing is an automated system that's used by measuring gas chromatograph mass spectroscopes of particles bound to another fiber. And then what we do is we have partition coefficients, and these log values, the ratio of the media to the particle binding, is essentially correlated to a set of 5 molecular descriptors. These molecular descriptors are the so-called Abraham descriptors that are widely used in REACH projects in Europe for predicting absorption chemical reactivity. So we're not reinventing the wheel here. What we're doing is applying it to the surface of a nanoparticle. And the basic molecular interaction forces, the Coulomb forces, London dispersion forces, hydrogen bonding, polarizability, and lone pair electron forming. We then did these models and then validated it with a set of 12 different probe compounds. So the basic model for a multi-wall carbon nanotube in this case is the partitioning between the meteor and the surface particle is described by 5 forces. This V term, wherever we're here, is the strongest, as you can see, by a factor of 4. This is lipophilicity, basically indicating for a multi-wall carbon nanotube that for a hydrophobic surface, obviously the fat-soluble compounds are going to bound to it. Hydrogen bonding is also an important component for the hydrogen bonding basicity. For other compounds, it might be the hydrogen bonding acidity. A pi term is a polarizability term, and this is actually relatively important in some cases for a number of different types of particles. And finally, the lone pair electron had minimal effects here because in a multi-wall carbon nanotube, they're actually shielded by the pi electron clouds. So the point about this is that you're looking at the material surface, and now you're coming up with a number of physiologically relevant parameters that would interact to binding of compounds. So what do you get? You essentially get an interface and a molecular signature of how a compound, for in this case, of a carbon multi-wall carbon nanotube, would rather interact with the nanoparticle or the water. So if you're a molecule, you could be a protein, you could be some other type of hormone. If you were very hydrophobic, you're going to bind to the surface of the particle rather than be in the water. If essentially you are a base, in some cases, you might interact more with the water. So you start getting a multi-dimensional parameter of how a specific particle would interact with a biomolecule. If you then look at the validation set, the model worked pretty well, which means that those 28 compounds are not unique. You could use other compounds to probe the same effect. And without getting into QSAR, we have a pretty reasonable area that this is a representative model for the number of chemicals we're looking at. If you then actually look at, for a nanomaterial, the correlation of this parameter to what would happen with our octanol water partition coefficient measured separately, you see a reasonable correlation. But again, we realize that there's other types of interactions occurring. It's not just the hydrophobic interaction. In the introductory paper that reviewed when our paper came out in Nature Nanotech, this diagram actually explains pretty much what we're trying to do. Is you're trying to come up with how can you look at the interaction between a carbon nanotube and a compound through the BSI index. We use these molecular descriptors, which are generally available for the specific compound, and the specific nanoparticle will have different correlative strengths to these various indices, and then you can essentially model, or could you predict what kind of compounds would bind to it. To show that, we looked at the correlation of the parameters to what would happen if we were looking at hormone binding to a nanoparticle, and what would the predicted partitioning of the hormone to the nanoparticle in a biological environment would be. Then we went out in the literature and dug out, did anybody ever look at this? And we found 3 cases where they in fact did look at that. And you can see reasonable now correlation. So without doing these kind of studies, if you have a nanoparticle, you could start looking at what would it be expected to bind to. And when you do that, we've done these descriptors for 12 nanomaterials. If we plot this on a compass plot, we realize that these nanoparticles are all different. Why? Because their surface chemistries are different. And because their surface chemistries are different, they're going to be binding to different type of biomolecules. So in addition to size, in addition to weight, and in addition to charge, you have properties of the nanomaterial that are going to dictate the type of biological interactions that may occur. So in conclusion, we know that nanoparticles distribute to tissues after systemic exposure, but patterns that are significantly different than after organic chemical exposure. Tissue uptake is particle dependent, shown by both the infused tissue studies and the PBPK studies. And the BSAI index correlates to the octanol water partition coefficient, but provides more information relatively to biologically significant molecular forces. This kind of an approach can be used to generate a molecular signature of potential nanoparticle interactions and then predict the absorption of biologically and environmentally important molecules. We hope ultimately to take this type of approach and essentially now incorporate that into that tissue uptake phase to determine what type of actual particle in the biological environment is actually being taken up into tissues. Thank you.